Good afternoon, everyone. This is CS310 Formal Languages and Automata Theory. After 1 week of a break, we will continue our lectures through online video lectures. Since we have given a short break, let's first start by making a review of the main concepts that we have covered so far since the beginning of the semester. We have mainly talked about regular languages, for this class of languages, we have seen three different types of computational models: deterministic finite automata, non-deterministic finite automata, and the regular expression model. Given a language, we have seen examples examples where we could construct a given DFA for the language, or an NFA, or a regular expression. And we have also seen that each of these computational models is equivalent. So the DFA computational model is equivalent to the NFA model, and NFA model is equivalent to the regular expression model in terms of computational power. What do we mean by computational power? We mean the following. If a language is recognizable using any of these models, then that language is also recognizable using the other computational models as well. So to generalize this, we have seen conversion algorithms to convert a given model, a given, let's say, machine in a computational model, to convert it to an equivalent machine in another model. So for instance, we can actually automatically convert a DFA to an NFA because we don't even have to do anything explicitly, since every DFA is already considered an NFA. For the other direction, we have seen an algorithm to convert a given machine in the NFA model into an equivalent machine in the DFA model. Similarly, for the relationship between the NFA model and the regular expression model, given a machine in the NFA model, we have seen an algorithm to convert it to an equivalent regular expression, and vice versa. Given a regular expression, we have seen a conversion algorithm that converts the regular expression into a machine that recognizes the same language as the regular expression. Okay, so the next natural question that comes up is every language regular? By considering this question, we will be thinking of the limitations of these computational models. So let's go with the definition of the finite automata, either DFA or NFA. Remember that each of these automata models, they are based on the following concept, that we have a finite number of states to recognize a given language or to solve a given computational problem. Since the number of states in these models is finite, the capabilities of these automata models should naturally be limited as well. So therefore, our answer to this question will be in the negative, that not every language is regular. But the next question then is, how do we understand whether a given language is regular or not? Or in terms of the language of the problems, if we are given a computational problem, how do we know if that computational problem is simple enough to solve it using one of these computational models? Well, actually, there's not an easy way of deciding this question, deciding whether a given language is regular or not. Is a given language L regular or not? This is our main question now. One hint to answer such questions is that we need to consider the language and try to see whether a hypothetical finite automata would have to be required to have to store indefinite amount of information or to do an indefinite amount of counting. Okay, this is just a hint, but let's consider this hint along the following example languages. Let's consider these two languages. L1 consists of strings W consisting of zeros and ones, such that number of zeros in W is equal to number of ones in W. Let's consider a second language, L2, which will look very similar. Again, this also consists of strings of zeros and ones, such that number of, this time we will be checking the number of substrings, number of 0, 1 substrings, 0, 1s in string W is equal to the number of 1 zeros in W. Now, if we consider these two languages, they look very similar. Both of them are trying to check the number of certain symbols or the number of certain substrings in a given string. But we will see that the first language is not regular, whereas the second language, L2, is regular. We give the example in terms of these two languages to emphasize the fact that we can use our hint that we use to try to guess whether a language is regular or not. Let's try to think whether the language or a hypothetical finite automata would be enforced to do indefinite counting or not. But while using this hint, we need to be careful for such instances. So both of the instances of the languages kind of seem to be requiring an indefinite amount of counting. To decide whether a string belongs to L1, we need to count somehow the number of zeros in the string and the number of ones in the string, and to see whether they are equal or not. Or if we had such a mechanism, then we could decide whether a string belongs to this language or not. Same goes for L2 as well. If we had a mechanism to decide to easily count the number of 0 ones in the string and the number of 1 zeros in the string, and we could just check whether those two counts are equal to decide whether the given string is in the language or not. However, the difference between these two languages is that the second one, although if we have such a counting mechanism, it's easy to solve L2 or to recognize L2, the language may not require that counting. That counting mechanism is not required for L2. We will see why recognizing a string in L2 doesn't require such a mechanism. Let's try to concentrate on a sample string that consists of zeros and ones. So let's rewrite L2, 0, 1 star, such that number of substring 0, 1s is equal to number of substring 1 zeros. Now consider a sample string W that consists of zeros and ones. Let's first concentrate on the first occurrence of any of these special substrings. Let's say that that first occurrence belongs to 0, 1, somewhere here. If this is the first occurrence of these two special substrings in this string, then this means that the prefix cannot contain ones. It should consist of zeros. Okay, so we have zeros all over here, and then we have the substring 0, 1 right in here. Now, let's say that in the following part of the string, if we want to create another instance, another occurrence of the substring 0, 1, so another occurrence of 0, 1. Let's see how this situation can happen, that we have an occurrence of the substring 0, 1 here, and later on we see another occurrence of 0, 1. Note that in order to have this occurrence, the second occurrence of the substring 0, 1, we need to see a 0 in our string. Okay, but when we see the symbol 0, what can be the preceding symbol in here? The preceding symbol in here, even if it's a 0, it will be preceded by zeros, but then at the end, at some point, we will see a 1, a symbol 1 in here. Okay, now once we see that symbol 1, we can see that this occurrence of the substring 0, 1, in order for this occurrence to be followed by another occurrence of the substring 0, 1, we need to see the substring 1, 0 somewhere in between. Okay, same goes for the other direction as well. This tells us the following, that if we consider processing the symbols of the string W one by one, at any point during the processing of the string W, we can have one of these three cases. 1. In the part of the string that we have seen so far, number of occurrences of 0, 1s might be equal to the number of occurrences of substring 1, 0s. 2. Number of occurrences of 0, 1s is 1 more than the number of occurrences of 1, 0s. Finally, number of occurrences of 0, 1s is 1 less than the number of occurrences of 1, 0s. Okay. Since we have just a finite number of cases that are possible, it should be easy to see that we can easily design a DFA for this language L2. Let's see how that DFA looks like. We have our starting state Q0. What should we do when we encounter a 0 at this initial state Q0? We need to record that information because we have now a new information stating that the part of the string that we have seen so far ends with a 0. This will be recorded at Q1. Now, what is the situation at Q1? In terms of these counts, number of 0, 1s and number of 1, 0s we have seen so far are equal, and the string ends with a 0. Okay? Now, if we encounter a 1 at this state, we should create yet another state to record this fact as well. The meaning of Q2 will be that, again, number of 0, 1s and 1, 0s that we have seen so far in the string are equal, and the string currently ends with a 1. Let's see what we should do when we encounter a 0 and a 1 at Q1. If we encounter a 0, nothing in the meaning of Q1 is changed, which is number of 0, 1s and 1, 0s is equal, and the string ends with a 0. But if we encounter a 1 when we are at the stage Q1, now we have a new type of information. This means that we need to create yet another state, Q3. Now the meaning of Q3 is that number of 0, 1s in the string so far is 1 more than the number of 1, 0s, and the string ends with a 1. What should we do at Q3 if we encounter a 0 and a 1? If we encounter a 0, let's think of the meaning. The number of 0 ones is now one more than the number of 1 zeros, and the string, actually if we encounter a 0, we now know that we have some string of the following format. We have 0 1, and then now we have encountered yet another 0. So now number of 0 ones is equal to the number of 1 zeros, and the part of the string we have seen so far ends with a 0. Well, this is actually the meaning that we associated with the state Q1. So we transition into the state Q1. What should we do if we encounter a symbol 1 while at 3? This means that in the part of the string that we have seen so far, number of 0 ones is one more than the number of 1 zeros, and the new symbol is a 1. So the last symbol of the string, of the current part of the string, is a 1, which is the meaning we have associated with Q3, so we loop. Okay. We should do symmetrical transitions on Q2 as well. So on Q2, if we encounter a 1, we should loop, because number of 0 ones and 1 zeros is equal, and the string ends with a 1. If we encounter a 0, we should transition into a new state. Let's call this Q4. What should we do at Q4 if we encounter a 1? If we encounter a 1, then the number of 0 ones and 1 zeros become equal, and the string ends with 1. If we encounter yet another 0, then the number of 1 zeros is one more than the number of 0 ones, and the string ends with a 0. Now, which of these states should we assign as the accepting states, since Q1 corresponds to the state where number of 0 ones is equal to what number of 1 zeros. Same is true for Q2. Number of 0 ones and 1 zeros is equal. These two states are going to be our final accepting states. Now, we have seen that we can design a DFA that recognizes this language L2, which means that to recognize the strings of this form, we actually don't need to do an indefinite amount of counting, so that by just storing information on a finite number of states, we can recognize strings of this form. We will see that the same is not going to be true for this language L1, which means that for recognizing such strings, it will definitely be necessary to keep track of indefinite amount of information. In this case, we need to somehow do an indefinite counting of zeros and ones. But such a guess, so this is currently just a guess, that this L1 is not regular, since it seems to require an indefinite amount of counting. But when it comes to formality, how do we formally prove that such a language is not regular? Or in general, how do we formally prove that a given language is not regular? To do this, we actually have a lemma called the pumping lemma. Pumping lemma for the regular languages. Let's first state the lemma. It says that if a language L is regular, if L is regular, then there exists an integer p, a positive integer p, such that if we take any string s inside this language with sufficient length, if a string s inside this language with length of s being greater than or equal to this p, which is also called the pumping length, then for any partition of this string s into 3 substrings, then for any s equals x, y, z, we are partitioning the string s into 3 substrings x, y, and z. We have to have 3 conditions that are satisfied. 1, consider this middle substring y. We should be able to pump this substring y as many times as we want and still remain in the language. Or in other words, the new string x, y to the I, z should be in the language L for all I greater than or equal to 0. This says that for any such partition of s into 3 substrings, this middle substring y, we should be able to repeat it as many times as we want, and the new string should still be in the language. Second condition says that length of y should be greater than 0, or in other words, y is not equal to epsilon. Third condition, length of x and y considered together should be less than or equal to our pumping length p. Okay, this is the lemma. Let's try to see a proof sketch of this lemma. How can we convince ourselves that this lemma is true? We will not do a full proof. You can find the full proof in your textbook, but we will just try to show a simple proof sketch. Now, our statement starts with the assumption that L is regular. If L is regular, then we know that there exists a DFA, let's call it M, that recognizes this language L. So L being regular implies there exists DFA M such that language recognized by M is the same as L, such that M recognizes this language L. Now, our next statement says there exists a positive integer p such that the following is satisfied. Now, we will pick p as a fixed number that depends on this supposedly existing DFA M. So let's pick p, the pumping length, to be the number of states inside this M. Number of states in M. Now, the following part of our lemma says, if we take any string inside this language with sufficient length, with length greater than or equal to p, let's consider any string s. Let's just write down every symbol of s, s1, s2, all the way up to sk. Each of these are the symbols of the string s. It has length k, and by this part of the lemma, we assume that k is greater than or equal to p. That is, the length of s is greater than or equal to this pumping length p. Let us try to imagine how this DFA M does its computation on this input string s. Remember that in the DFA model, the computations happen through a computation path. So we basically start our computation at the starting state. Let's call it Q0, and then next, this first symbol of the string S1 is processed through a transition. We go to another state, which processes this next symbol S2, transition into a state, and so on until at the end we process this last symbol of SK, and we should be arriving at one of the accepting states of our machine M. Why? Because the string S is accepted by this machine since S is inside the language. Okay, so this is our computation path. Let's call it C of our machine M working on this string S. Now note that in this path there exists at least P many edges. If there are at least P many edges in here, the number of nodes on this path is number of states in this path C is greater than or equal to P plus 1. Now what is the significance of this? We know that P stands for the number of states in our machine, and on this path there are more than P states, which implies that by the pigeonhole principle it has to be the case that one of the states, at least one of the states on this path should be repeating. So by pigeonhole principle, a state should be repeating in our path C. Now let's try to redraw our computation path C. We will pick first such repeating state, Qi. With Qi, our computation path looks like the following. Q0 is our starting state. This transition consumes S1 and so on. At some point, we will be transitioning into the state Qi. We continue. Again, we should be transitioning into the same state Qi. We continue. At the end, we end up at the accepting state. Okay. This should be how our computation path C looks like. Now, the significance of this computation path is that if we have such a path, the machine M itself, part of the machine M itself, should look like the following. We have Q0, we have Qi in here in the machine, we have our QAccept corresponding to this accepting state somewhere here in the machine. In our DFA-M, there must exist a sequence of transitions from Q0 to Qi. It corresponds to the sequence of transitions in here. We need to have a loop of transitions that starts at Qi and goes back to Qi, corresponding to this part of the path. And corresponding to this part of the path, there must exist a sequence of transitions that leads us to Qa. Now, let's denote the substring consumed by this first part of the path with X. Let's denote the substring corresponding to the string that is consumed through this loop as Y. And let's denote this part of the path as Z. Then, now at this point, we can check those three conditions of our pumping lemma, which were 1. X, Y to the I, Z should be in the language for any I greater than or equal to 0. By looking at this figure, we should be able to see that this is true, because once we arrive from Q0 to Qi by consuming this substring X, we can repeat this Y loop as many times as we want and then consume the part of the substring corresponding to Z and arrive at an accept state. So any such string will be in the language because any such string is accepted by the machine. 2. Length of y should be greater than 0. Well, we have seen with the discussion above that there exists such a part of the path that starts at some state qi and revisits the state qi. This means that this part of the path corresponds to a substring that is not empty. So y is not epsilon. Y is not epsilon. Finally, for the third condition, the length of x and y together should be less than or equal to p. Why is this true? Because we have picked the first repeating qi in our computation path, which means that in this part of the path in here, when we consider x and y together, there exists no repetition of the states, which means that in this part of the path, we can have at most p plus 1 many states, considering the qi repeat as well, which implies that the number of transitions in this path will be at most p. Now, this proves us the pumping lemma. In the next lecture, we will consider how we can use pumping lemma to prove certain languages are not regular, and we will see many different examples of applying pumping lemma to prove such non-regularity.